Welcome to Maths with EJD. We are still talking about differential equations, particularly first order ordinary differential equations. And in this video, the focus is on Bernoulli's ordinary differential equation. So, for an overview, Bernoulli's differential equation is a first order nonlinear. In the previous video, we had considered a first order linear differential equation that could be solved using integrating factor. But in the case of Bernoulli, we have a differential equation which is the first order nonlinear differential equation of the form dy dx plus p of x y equals q of x y raised to power n. Okay. Now here, this looks almost like the equation we considered for, in the previous video, because we have dy dx, we have p of x of y, we have q of x. The only difference lies in this y raised to power n. Okay. So, and because that y is raised to power n, that makes it non-linear. All right. So here, so where p of x, where p of x and q of x are continuous functions of x. Okay. And n is not equal to 1, because if n is equal to 1, that would be, the equation would be linear. Otherwise, the equation is linear. Okay. So Bernoulli is non-linear. So it has to be 2 upwards. Now, the next thing we'd like to look at would be the solution method. What is the solution method to a problem like this? Okay, so it looks so much like what we did the other time for using integrating factors, except for the y raised power n, which makes it non-linear. But then to solve the Bernoulli equation, okay, so the first thing we do is to divide through by y raised to power n. We divide through by y raised to power n. Of course, that is based on the assumption. That is based on the fact that we are assuming y is not equal to 0, because if y is equal to 0, we can't divide with that. It will be undefined. So now look at the original expression again. We have dy dx, okay, plus p of x y equals q of x y raised to power n. So if you divide through by y raised to power n, so you have 1 over y raised to power n dy dx plus p plus, say, y 1 over y raised to power n p of x y equals 1 over y raised to power n q of x y raised to power n. So this just cancels this out. And then here we have y raised to power minus n dy dx, okay, plus, of course, this is y raised to power minus n p of x y raised to power 1 equals q of x. So we have q of x left there. So we can write this as y raised to power minus n dy dx plus p of x y raised to power 1 minus this n here. So putting these two together, we have y raised to power 1 minus n, and that's equal to q of x. Now, having divided through by y raised to power n, see the expression we have. Now, the next thing we want to do is to, so we now want to introduce a substitution. We introduce a substitution. And so that will lead to a transformation where we have v equals y raised to power 1 minus n. So you see, we have y raised to power 1 minus n here. So this automatically is like v, okay? So, and if that is the case, if we now want, so we want to replace So now y is y raised power v is y raised power 1 minus n. So we also need dy dx, right? So we know first of all here that dv dx is going to be something like dv dy times dy dx. So from here we can have our dy dx, okay? So that means that dv dx would be equal to dv dy. If we differentiate v with respect to y, 1 minus n will come down. We have y raised power 1 minus n minus 1. So we have differentiated with respect to y. And then this is implicit now. So we have dy dx. Okay. So this cancels this out. So we have dv dx equals 1 minus n y raised power minus n. Okay. dy dx. So this is dv dx now in terms of dy dx. So what if we want to make dy dx the subject of formula so that we can easily replace up there later on? So we can try that. So we can do this transformation that this becomes, this will now be like 1 all over 1 minus n y raised power minus n dv dx, okay, equals dy dx. So that's if we transfer all this to this other side, okay? So we do the transfer down here. So we can say that dy dx in that situation would be 1 over 1 minus n y raised power n dy, dv dx, okay? dv dx, okay? So that could lead to the total transformation of that whole expression like that, okay? But then let's rest that and move on to other things. We'll revisit that later. Okay. So, okay. With all this that we have, right, we can rewrite that. So if you rewriting, okay, I guess I want to color code at this point. So rewriting the original equation, writing the original equation in terms of v, okay? We have this expression now, right? So instead of dy dx, okay, here we have y raised by minus n dy dx, right? So we can say this is y raised by minus n, okay, which was there before. But now dy dx has a new expression, which is 1 over 1 minus n, okay? And then y raised by n dv dx, wants dv dx to be there now. So that has replaced that dy dx. Then we have p of x. So we have plus p of x. Y raised by minus 1, y raised by 1 minus n is now v. And this is equal to q of x. So that is what we have based on the current realities. And if that is the case, of course, yn cancels y raised by minus n. And we have 1 over 1 minus n dv dx, okay, plus p of x v equals q of x. So we can still tidy things up. That 1 minus n can still go and divide. So if we multiply through by 1 minus n, right? Okay, so we have 1 over, we have 1 minus n times 1 over 1 minus n dv dx, okay, plus 1 minus n p of x v equals 1 minus n q of x, like that. Okay. So because this cancels out, and we have dv dx now plus 1 minus n p of x v equals 1 minus n q of x. So we have this expression now in terms of v. Okay. So with this in place now, we have a new expression. So now we can say this is now a linear. So this is now a linear differential equation, just like the one we did in the previous video where we could use integrating factor. This is now a linear differential equation, okay, in V. which is solvable using the integrating factor method, using the integrating factor method. Okay, because if you look at it, right, this is like so this is like dv dx, and this whole thing is like your p of x, and this is like a q of x if you look at it that way. Okay, now that that is settled, can we check this out? Okay, so let's look at an example. So imagine that you need to solve the Bernoulli equation, dy dx. Of course, it's first order, 2 over x y equals x cubed y squared. It's nonlinear because of the y squared. If you have y raised by 1, then it becomes linear again. So imagine that this is what you have, and we need to deal with this. So the first step you want to take, step 1, because of the modification we've done before, the first thing we want to do is to identify parameters based on the standard form. Identify parameters. So here you have dy dx, okay, plus 2 over x y equals x cubed y squared. So if you compare this with the standard, which is dy dx plus p of x y equals q of x y raised power n, what do we have? So this simply tells us that p of x is equal to 2 over x, because that's what you have in front of y. Then you also have q of x to be what is in front of x, y squared, that's x cubed. And now our n is equal to 2 because that's the power of y. Okay, n is 2. So this 2 is this n. So q of x is this x cubed. Then p of x is this 2 over x. So we have clearly identified those. And now once we identify the parameters, the next thing you want to do is to go for the substitution. That's step 2. Step 2, you go for the substitution. Okay, so definitely here now we define our v. Now the substitution we do is v is generally v is y raised by 1 minus n, from what we did generally. So v now is equal to y raised by 1 minus 2 because n is 2. So v is equal to y raised by minus 1. Why is n 2? Because the power of y is n, which is 2. So you have v to be y raised by minus 1. So we could actually now get dv dx. So dv dx would be dv dy times dy dx as an implicit expression. So that dv dx would be, so if you differentiate dv dy, that means differentiate y raised by minus 1 with respect like that. So we have minus y raised by minus 1 minus 1 dy dx. So that tells us that dv dx is equal to minus y raised by minus 2 dy dx. So we have this expression right now. So if that is the case, then we can have so if this is the case, right? Of course, yeah, we have this. We can arrange this in the standard form. So rearrange to standard linear form, based on what we had done before, right? So this now becomes dv dx plus 2 over x v. If you do what we have here, like this general expression now. So this is dv dx plus 1 minus n is 1 minus n is minus 1. Then we have p of x. Okay. So we have okay, okay, this is rewriting. Okay, this is still what we have. So we have to rewrite the original equation before we do this, sorry. Rewrite the original equation. So we have to rewrite the original equation. So if you follow that format, right? So we rewriting the original equation, okay, we have minus dv dx minus 2 over x v equals x cubed. Okay, but this is definitely not the original form. So if we do all the substitution like we did before, we get this, right? So we can now rearrange to standard linear form. So if we do that now, it means you're multiplying through by minus 1, so it can be in standard form. So we have dv dx plus 2 over x equals minus x cubed. Importantly, so because you're multiplying through by minus here, so you have this expression now. So this is now like the standard form we have always been used to. So this, okay, sorry, this is 2 over x v. Okay, this is 2 over x v minus x cubed. So now this looks like what we would usually know as P of x, and this is now Q of x for the actual linear form, not the Bernoulli type now. But the transformation brings us to the linear form at the end of the day. So we go for the next step we need to do right here. We go for step 3. So in step 3 now, so we solve linear equation, solve linear equation. So we have identified all the parts, right? So we need to get the integrating factor. So the integrating factor, now that it is linear, so we can do integrating factor. So the integrating factor, IF, is mu of x, which is equal to integral e raised to power the integral of p of x dx. Now p of x is 2 over x as we have identified up there. So mu of x is equal to e raised to power 2 over x dx. All right. And as we know, mu of x here would be e raised to power 2 integral of 1 over x dx. And when you integrate the inverse of this kind of expression, you're going to get ln. So e raised to power 2, and that should be ln of x. All right. We don't have to care about the c because c comes at the end of the day. So mu of x will now be e raised to power from the law of logarithm ln x. Of course, because once 2 goes there, so the that absolute value is not necessary anymore because 2 guarantees that it is always positive. And because e cancels linear, right? So mu of x is automatically x squared. So we have x squared, for the integrating factor, since the equation is now in linear form. So we have integrating factor. So what we are doing next is to multiply. So multiply through by the integrating factor. Multiply. Let me call this star so we can, for reference, so this is star. Multiply equation star. That's our linear form. Multiply equation star through, okay, by mu of x equals x squared. That is our integrating factor now. So that means we have x squared dv dx, all right? So we have x squared dv dx plus x squared. Is it plus even? Yeah, I think it's plus x squared times, what is there now? Plus x squared 2 over x v, okay? X squared 2 over x v equals, then right-hand side, we have minus x cubed. So we have x squared times minus x cubed that we have up there, okay? So now we can say this is x squared dv dx. 1 of x cancels one of this, so we have plus 2xv equals minus x raised to power 5. So this is the expression we have now. But then this can be written in shorthand form like ddx into 2xv, okay? Such that, ddx into mu x, right? So that is mu x v equals minus x raised to power 5. So that means we have ddx into mu x is x squared v, right? Equals minus x raised to power 5. Now, so of course this is correct because if you differentiate x squared, you get 2x with v. If you differentiate v, you get x squared dv dx. So we are good to go. So with that in place now, we can integrate both sides. So say integrating both sides, integrating both sides. Okay. So we have integral of d dx into x squared v dx equals integral of minus x5 dx. Okay, so dx cancels dx, and so we have integral of d of x squared v. Okay, d of x squared v, and that is equal to minus integral of x5 dx. Okay, so of course, when you integrate d of anything, it gives you just that thing. So you have x squared v equals minus. When you integrate x raised to power 5, you get x raised to power 6 all over 6 plus integration constant c like that. And from here now, v becomes our subject of interest. So we have v now. You can divide through by x squared. So we have x squared v all over x squared equals minus x raised to power 6, x raised to power 6 times x squared down here plus c all over x squared. Okay. So this cancels out. So we have v is equal to minus 1 over 6 x raised to power 4, because 2 of this will cancel 2 of this and you have 4 left, plus c all over x squared. So I can even write this better and say minus x raised to power 4 all over 6 plus c all over x squared. So that is v. But we did not start with v, right? So we have to go back to the beginning where we got that v from. So we can go ahead and say that now step 4, we now do back substituting, or backward substitution, or we say back substituting v for y raised by minus 1. All right. So since v is y raised by minus 1, so we now have instead of this v now, we have y raised by minus 1 equals minus x raised by 4 all over 6 plus c all over x squared, right? Yeah, so we have that. So we are, now we are looking for y. Now we're looking for y. So we now have, okay, we can tidy things up a bit here, right? So we have y raised by minus 1 equals, or better still, I can say this is 1 over y equals, LCM here is 6x squared. So 6x squared is x squared. So x squared times x raised to power 4, that's minus x raised to power 6 up there, plus x squared in x squared, that's 6. So we have 6c. So since we have 1 over y, so we can actually get y equals 6x squared all over minus x raised to power 6 plus 6c. Okay, so we now have this value for y. So at this point now, we can say, therefore, the general solution, to the given Bernoulli equation, is what we have up there. Now that's called that y of x, and that is equal to 6x squared. That is 6x squared all over, if you like, 6c. That's 6c minus x raised to power 6, right? 6c minus x raised to power 6. So this is the general solution. So of course we can graph this to see what it looks like. So this is since it's a general solution, so we are going to have a family of solutions depending on whatever the value of x is. So we have 6x squared all over 6c minus x raised to power 6. That is what this is about. So if we had an initial condition, we could now get the exact with the particular solution, like it's called. So here now we have 6x squared, all right, divided by, okay, not this way, okay, divided by 6c, okay, minus x raised to power 6. So that's c. We need a slider on the c. So see, you have all the function all over the place. So if we So if you start from -10, see what it looks like. And then by the time we continue, it keeps stretching out, stretching out, stretching out. You see, it keeps stretching out. So it keeps stretching out. Then at some point, we begin to have jumps. We have asymptotes, like it's called, right? You have points of discontinuity, and then it grows like that. So it means there's a particular threshold there where there's no point, where the points of continuity start appearing. Okay, imagine this now. At what point does it stop appearing? I think that's when we have like -0.2 or something like that. Okay. And then, all this keep going. So we can visualize it this way. Now look at, just like I like to do, right? What if, let me start from my usual -3 and all that. So not using a slider now. So let's say 60, 6C is -3. Okay. This is -3. So see what happens, -3. So what if I say it's now -2? See what we get. Then I bring it down and we have -1. See what we get. So it's stretching down. And then I come again and we have, instead of -1, now this is now 0. Okay. This is 0. So see what that is. So it goes all the way down, like to some kind of infinity, so to speak. And then we now come down and 0 becomes 1. So we now begin to have those discontinuities. So all these are their solutions to the function, because this is a family of solutions depending on whatever the value of C is. So what if we take 2? So you also get that. And then let me stop at 3. So I always like to go from -3 to 3. So I have 3 here now. So you have this family of solutions as the solution to that problem that we've been looking at. So all the solutions fit the problem for sure. So that's how to visualize that, by graphing. Okay, so at this juncture, let's talk about some practice questions, and we have quite a lot. So you can try your hands and be sure you really understand the concept. Okay, so I'll just say a general solve, then I'll just list out the problems. So solve the following. Solve the following. 1, dy dx plus y equals xy squared. 2, dy dx plus 3 over xy equals x squared y squared, x squared y squared. 3, you have dy dx minus 2 over x y equals y cube. Okay, so in that case, q of x is definitely 1. Okay, and n is 3. Then number 4, what if you need to solve x dy dx plus y equals x cube y raised to power 4. So the hint here is divide through by x first of all, so that this x goes away. So you can have that in a standard Bernoulli form, and then you can do other things. Then what if you have number 5 to be dy dx plus y all over x equals x squared y raised to power half. Now, your n is half. Okay, I want to try that. And then what if you now also have dy dx minus y over x equals x cube over y. Okay, x cube over y. So here, that's y raised to power -1. So your n is -1. So you also want to check that to see what it looks like. We have a 7th question, a lot of questions. So dy dx plus tan x, dy dx plus tan x multiplied by y. Okay. Okay, let me put this in bracket to show that it's not part of the tan, right? So, and that is equal to y cube. So your n there is 3. We can have an 8th question, which is x dy dx, okay, plus y, x dy dx plus 2y equals x squared y raised to power -1. We have question 9. It's a lot. So we have dy dx plus y ln x equals xy squared. And finally, question 10, we have dy dx plus 2 over xy equals e raised to power x y raised to power 3. So try your hands on this and let me see your answers in the in the comment section, either on YouTube or on Facebook. Try this out. If you have an issue, you can let me know. So if you in the comments also, let me know how helpful these videos are for you. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. I may be able to find time to do that along the line. Then, of course, if you have not subscribed already, please go ahead and subscribe because there's a lot more coming. So, for instance, after this, I think we'll be talking about exact equations or something like that. And you don't want to miss any of that. So, and there are a lot of materials already on this channel, talking about matrices, basic equation, basic differential, basic calculus, set theory, vectors, probability statistics, linear programming, a lot. So you don't want to miss any of this. So be sure to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.